পড়ানো যতটুকু দিদি।
Okay, okay, okay. So, last class we have discussed some numerical problems regarding weight average and number average molecular weight of the polymeric substances. So, now we are moving towards the determination. We are moving towards the determination of the molecular mass of polymeric compounds. So, first of all, the most important one, the most important part is that the osmotic pressure. So, the determination of osmotic pressure. Sorry, determination of the molecular mass by osmotic pressure. So this is today's topic that we are going to discuss, that osmotic pressure for the measurement of molar mass. Osmotic pressure for measurement of molar mass. So first of all, we are going to discuss something that osmotic pressure is one of the four colligative properties that is used to determine the number average molar mass of a sample of polymer. What it calculates? It actually calculates the number average molar mass. Okay, it actually calculates the number average molar mass. So osmotic pressure is one of the colligative property which is used to determine the number average molar mass. So what is number? Just a minute, extra minute. Okay. So it determines the number average molar mass of polymer. So there are other three methods also, such as relative lowering of vapor pressure, elevation in boiling point, depression in freezing point. So these three processes are not that sensitive as sensitive the osmotic pressure method is. So the osmotic pressure method is the most used and gives you the most accurate value of the molar mass in comparison with the other three processes, other three colligative properties. So thermodynamically, so thermodynamically, derivation of osmotic pressure derivation of osmotic pressure of a solution. So in most of the cases, we use osmotic pressure method to determine the molar mass of IEA polymeric compounds. So thermodynamically, I can say the osmotic pressure of a solution result into the expression, and this is a known expression for you, that pi 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 v equals to RT ln 1. This is a very known equation to you. But I am writing it such as pi v star L comma m. I think 1, I think সবচেয়ে ভালো হয়, it's good that if you expressing the molar volume na actually, so equals to minus RT ln A1. So maybe this is the equation 1, that where this V1 is the molar volume of the solvent. Is the molar volume of the solvent. So this is the molar volume of the solvent, and A1 is its activity in the solvent, and A1 is its activity in the solution. So there are some assumptions, some approximations are there regarding the osmotic pressure. I am going to discuss this approximation one by one. So for a dilute solution, I will discuss it one by one by giving a particular number. So for a dilute solution, that the equation 1, that is the first equation that we have written, that pi v1m star, pi v1n star, okay, equals to minus rt ln a1, and a1 is its activity in the solution. So for dilute solution, equation 1 is simplified by using such as the following approximations. Now I am going to discuss the approximation. That is, what kind of approximations that we made to determine the molar mass of osmotic pressure. So first one is that these 3 or 4 approximations are very important. So first of all, the first approximation is that the activity A1 of the solvent is equal to its amount fraction, that is A1 approximated to x1, that is the activity of the substance is approximate to mole fraction of the substance. So ln A1, that is written in the equation 1, is approximated to x1. Remember that this x1 A1, that is suffix 1. Suffix 1 is always for solvent and suffix 2 is for solute. So I'm writing the statement that the activity A1 of the solvent is equal to its amount fraction, that is A1 is approximated to x1, okay, such that I can say ln A1, that was the mathematical, that was present in the mathematical relation which was derived thermodynamically for osmotic pressure. So A1 is approximated to x1. So the second approximation is that since mole fraction of solvent and mole fraction of solute is equals to 1 always. This is a universal truth. It's always. So we can write what we can write. We can write that is ln x1 equals to ln 1 minus x2. This is the expression for x1 that we can get from the above equation. So this is equation 2. Now, in this equation, where ln x1 equals to ln 1 minus x2, ln x1 is equals to ln 1 minus x2, this equation. So if we solve the series, that is, we can say this is a log series from your higher secondary syllabus, x2 plus x2 square by 2, you know that it can be written like that, x2 cube by 3, and it is an infinity series, and this is equation 3. So for dilute solution, from this approximation we can write for dilute solution where the x2 is very small, sorry, where the x2 is very small, we retain only the first term and the neglecting the second term, only the first term and neglecting all the term. So what we can write? We can write ln x1 equals to minus x2 only, and we have neglected all the terms, that is x2 square. If the logic is that if x2 is very small, if x2 is very small, then the square of x2, it is much smaller than that of it. Okay, so for dilute solution we can write this, and this is our equation 4. Don't worry, I will going to finish this total scenario within 10 to 12 equations. So almost I have written 4 equations. Now number 3, assumption
স্যার
number.
একটু একটু উপরের জায়গাটা।
Now the assumption number 3. Should I proceed?
ইয়েস স্যার।
So here we can say that since the solution is dilute, since the solution is dilute, so what we'll have, we will have a simple assumption, that is the number of moles of solute is very less than number of moles of solvent. As the solution is very much dilute, we can have number of moles of solute present in the solution is very smaller than that of the numbers of moles of solvent present in the system. So we can write, that is what we know, x2 equals to x number of moles of the solute divided by total numbers of mole, that is number of moles of solute plus solvent. But as N2 is very smaller than N1, N2 is very smaller than N1, I can approximated it N2 divided by N1. So actually I am approximated N1 plus N2 is very close to actually N1. That is what I am approximated. The N1 plus N2 is very close to N1. And number 4, the fourth assumption for the process. And the fourth assumption that for the dilute solution, for the dilute solution, we can have V, number of moles of solvent plus into V1, comma P into M, that is pressure into mole. So actually PM stands for partial molar. লিখে রাখা ভালো, PM stands for partial molar. Partial molar plus N2, this is for solute. This is approximated to as for dilute solution, the number of moles of solute is very less. So we can say N1, this is our V1. Partial molar, we will not going to say it partial molar quantity right now because the amount of solute present in the system we have neglected, as N2 is very smaller than that of N1. So only the first term of the equation remains. Only the first term of the equation remains. This is maybe equation 6, I say. This is 5. Yes, so this is 5. And what we have only the equation 6 here, and which contains only the molar volume of the solvent, and this is the molar volume of the solution, as we have neglected the amount of substance present, as we have neglected the amount of substance present in the system. Okay, where, and this approximation is very important. If you have any difficulty to understand this, just let me know, I'll discuss it again. So V1 m star is the molar volume of the pure solvent. Molar volume of the pure solvent. Now, with this expression in equation 1 is modified to now with this expression equation 1 can be written as equation 1 can be written as what we can write, that is pi v. So V1m. So here actually V equals to N1 V1m star. So V1m it we can write in place of V1m star. We can write V by N1. We can write V by N1. Again, it equals to minus RT in place of A1. As I have said that in place of A1 we can write N2 by N1. Okay, so from this equation, we can conclude that pi equals to N2 by V RT, as N1 is subtracted from both the sides, and here N2 by V is actually C, that is the concentration. So, oh, this is not small pi, this is I'm using. So this expression is question 7. Now I am going to use this expression first. So first I have determined which theory I am going to use to determine the molar mass of polymeric solution. Now a polymer solution does not behave as an ideal solution due to large difference in molecular volumes between polymeric solute and low molar mass solvent. So that's why we can say a polymer solution does not behave as an ideal solution, probably due to the. So this is the one of the most important feature of polymeric solution. This is that they have a very large molar mass. So ideal solution difference due to large difference in molecular volumes between polymeric solute and low molecular mass solvent. So now the equation 3, it is accounted. Now the equation 3, what is equation 3? I also have to see what is equation 3. Now this is the equation 3, that is the series. Now the equation 3, I can write by not truncating any term, that is I am not neglecting any term. What we can write? We can write pi V star 1m by not truncating equation 3. What we can write, that is RT. Okay, RT, that is log, that is x2, the coefficient I have written, plus 1 by 3. So this is our equation 8. So what I have done, I have actually written the equation 3 in terms of that I have calculated the last equation, equation 7, and put the value of concentration in terms of that, where B prime and C prime are respectively known as second and third viral coefficients. I'm writing that B prime, C prime are known as second and third virial coefficients. So now we are going towards our approximation that we have made for the process, that if the solution concentration is expressed, if the solution concentration is expressed as mass of solute per unit volume, per unit volume of solution, so we'll have what we'll have a very interesting, a very, we'll have a very interesting assumption that we have made earlier, that x2 approximated to n2 by n1, as I have neglected all the I have neglected the n2 plus n1, that is, as n2 is very very smaller than that of n1, so I can say n1 plus n2 tends to n1, so the mole fraction of the solute can be expressed in as n2 by n1. So this is the equation 5 that we have used or we have developed earlier. So now we can write that which on using the expression, which on using the expression so which on using the expression I can say that is n2 equals to m2 by m2, and that is weight taken by molecular weight, that you know what is mole number, and n1, that is the number of moles of solvent, I can say v by v1 m, that is molar volume of the solvent, by using equation 6, it actually becomes x2 actually becomes So x2 equals to what I can write, that is m2, n2 I can write m2 by m2 and v by v1 into m. And this is the major approximation that we are making. This is the most important approximation that we are making. So what I can say, I can say suppose m2 by v, I am writing like that, m2 by v, and v, that is the molar volume of the solvent, and the m2 remains as denominator. So the upper part, that is m2 by v, that is actually c. This is our c2, mass per volume, বা mole per volume, the gram per volume, whatever it may be. M is, if m is the weight, v is the volume, then it is gram per volume, gram per liter, gram per ml. Okay, and this is the molar volume of the solvent divided by m2, and this equation is given as equation 9. Now substituting equation 9 in equation 8, equation 9 in equation 8, that is putting the value of x2 in place of this. This is equation 8. Now I am going to putting the value of x2 in place of x2, that is 1 by 2 b prime x2 square and all that. I'll just write two terms, not more than that. So this is the molar volume. Now RT, and in place of x2 I am going to write this thing. So this is C2 V1 M star, that is M2 plus half B prime, that is C2 by V1 into M star by M2, this is whole square, and this is our equation. I have almost completed that. Now from the equation, what we can say, we can say just rearranging this equation, I can write, by taking C2 out of the equation from the right hand side of the process. So I can write C2 here and RT, okay, and RT equals to, so there is no C2 term present in the first term of the first term in the parenthesis, in the third parenthesis there is no C2 term will present, so it is only 1 by m2. Okay, now 1 v1 m star will come out from the bracket as a common, and it will cut from the right hand side and the left hand side of the equation, so it will remain 1 by m2 only for the first term, and for the second term it is 1 by 2. If anyone have any problem, just ask me. C2 has eliminated, there is c square, so 1 C2 remains, 1 v1 prime remains, so it's become v1 star into m by m2 into C2. So this is the part, and retaining, just a minute, just simplify it little more. 1 by m2 plus this total term 1 by b prime V1 molar by M2 square. This total term, it has a square, yes. The total term I am considering as B. This total term is B, so BC2 plus dot dot. So retaining only the first two terms on the right hand side as higher terms are insignificant, so we can write retaining only first two terms. I can say, oh, sorry, I can say TRT 1 by M2 plus this C2. This is C2. Okay.
So retaining the WRI something.
Hmm? Retaining only first two terms.
Retaining means what?
Retaining means only I'll keep the first two terms only, and other higher terms will be neglected. I will keep the first two terms only. That is in this equation where pi by C2RT equals to 1 by M2 plus 1 by 2 B prime V1, that is the molar volume of the solvent, into in molar volume of the solvent into C2 by M2 square, that plus dot dot dot, there are higher order terms too, that is 1 by 3 C prime, 1 by 4 D prime and all that. So as the higher order terms are insignificant because it is a square, so it becomes very less. So I am considering the first two terms, that is 1 by M2 plus 1 by 2 B prime V1 M M2 square C2. And I am also considering the B prime V1 star prime M M2, that is the molar volume by mass, this constant as a single B only, not as B prime. So retaining the first two terms,
Retaining spelling the sir.
yes, RETAINING, it is okay.
Okay, sir.
So this is equation 10 and this is equation 11 what we have. Now equation 11, now equation 11 that we have uh, derived,
Sir, 10 Gunda.
this one is 10. Okay, predicts that uh, sorry, for a dilute non-ideal solution, dilute non-ideal solution, and the graph between pi by C2RT and C2, definitely it should be linear, and C2 is linear, is linear with slope equal to the with slope equal to the second virial coefficient B. Second virial coefficient B, and from the graphical representation and intercept equal to the inverse of molar mass. Inverse of molar mass. M2 of the solute. Now, what I'm actually going to say, that if I consider if I consider this equation pi by C2RT, if I consider this equation pi by C2RT equals to 1 by M2, 1 by M2 plus BC2. If I consider this equation as I have discussed, and I am considering this term as y, and I am considering this term as c, this b is m, and c2 as x. So if I plot a curve, if I plot a curve, okay, just a minute, just a minute, just a minute, just a minute. This is the most prolific way to draw a curve. So if I draw a curve by using these parameters, then what I have a straight line. I have a straight line, and the curve is plotted against pi by C2RT. The curve is plotted against pi by C2RT and C2. This is the x-axis, this is the y-axis. Okay, so this slope is b, this is the second virial equation, and if I extrapolate this curve, this intercept will give you the inverse of m2. So from this intercept value, you can easily calculate the molar mass of the solute present in the system, that is the molar mass of the polymeric solute. Am I clear with my point? Am I clear with my point?
Yes, sir.
Okay.
Yes, sir.
So here I am stopping the recording. Just a minute.